Welcome everybody, thank you for coming to see my talk. Today I'm going to talk about some recent results that we have been obtaining in the thermal spin current generation in the multifunctional ferromagnetic insulator gallium iron oxide. So this work has been done in collaboration with people in Santiago de Compostela, so in Jena, and people from Strasbourg. Our group, I'm working currently in the Institut Jean Lamour in Nancy. So we are facing exponential growth in the amount of data that we need to store and operate, and we are having 50 times more data today than we had 10 years ago. So basically, the 90% of the data that we have currently has been created in the last 2 years. So we need faster and more efficient ways to store and operate with data. And to do that, we can use spins. Spins can give us another degree of freedom in our devices, from spin orbit effects to the play with electric fields, or using thermal gradients to obtain energy, or many other different physics that we can take advantage of to create new devices and new solutions for this challenge that we are facing. So to do this, we propose the use of this multifunctional ferromagnetic insulator, which is called gallium iron oxide. From now I will use GFO in short. So this material has an orthorhombic structure where the oxygen anions are arranged in a double hexagonal closed peg stacking along the z-axis. So there are 4 different cationic sites which are occupied by the gallium and the iron cations. And the origin of the ferromagnetism or the ferrimagnetism in this material is related with the disorder in the iron occupation. So it's very interesting about this material. It's that it's insulating, which will allow us to work with low Joule heating in some applications. And it's also very interesting that it's a room temperature bulk multiferroic, which will give us more opportunities to prepare or to fabricate new devices with additional functionalities. So our colleagues in Strasbourg have prepared high-quality epitaxial samples of this material, GFO. GFO is grown on STO111 substrate, and it's grown in the 001 direction, with platinum also in the 111 direction on top of it. We find that we have very low roughness in the platinum GFO interfaces and no interdiffusion, as you can see here. And also you can see by the low oscillations that we have high crystalline currents, as also can be observed here. So basically we have very high quality samples, and from here I will explain very briefly spin magnetoresistive effects in this GFO platinum layer. So I will only discuss about the longitudinal resistance. If you want to see more, please just go to this recent paper that we have published. And in the longitudinal resistance, we have mainly 2 different contributions. One coming from the magnetic proximity effect anisotropic magnetoresistance, and another effect from the spin Hall magnetoresistance. And as you can see, if you measure this as a function of the external magnetic field, you will see this typical behavior coming from the saturation of the anisotropic magnetoresistance or spin Hall magnetoresistance, and basically in this configuration both contributions are impossible to distinguish. So then the only way to separate them is, as you can see here, differentiate by angular measurements. We will do that next. But if we look at the total contribution and how it depends on temperature, we observe that 120 Kelvin there is a change in the behavior of the conduction, and this temperature, some people can argue that this is due to weak antilocalization, but this is a temperature which is too high for this. So we believe that this is a fingerprint of the spin orbit properties of the GFO manifested in the GFO platinum interface. So as I said, we can now try to disentangle the proximity effect coming from the anisotropic magnetoresistance and the spin Hall magnetoresistance in our bilayer, and we observe that at all temperatures the spin Hall magnetoresistance is dominating, and also that the proximity effects are almost negligible at most temperatures. From here we also obtain that this spin Hall magnetoresistance has a similar magnitude that the one typically observed in yttrium iron garnet platinum and yttrium iron garnet palladium systems, which are more or less the best systems that we can use in terms of ferromagnetic insulators for ferromagnetic spintronic applications. So we have a very nice system in which with which we can play, and in addition to having this ferromagnetic insulator material, we also have something to play with its multifunctional properties. Okay, so let me now discuss a bit about the Thermospeed transport in GFO. So first, let's play with the jig platinum system, which is the classic system in spin caloritronics. And what we are doing new here is we are preparing devices by photolithography to measure the thermospin voltage in a very controlled way, in which we can estimate all the parameters of the system. So this is how this looks. Normally, you have a gold heater, which is you can apply a thermal gradient out of plane or in plane if you come here. Then this heater is isolated by an insulating layer, and then you have your jig platinum sample below, in which you can measure the voltage that comes from the spin current injected into the platinum. So if you measure this as a function of the applied current in the heater, you observe that there is a linear dependence of the saturation voltage as a function of the heater, the power applied to the heater. This is what we usually should expect from a spin-Seebeck effect. And then we can move to study in a more careful way what are the temperatures and all the properties of our system to be able to quantify properly. So first, what we can do is have a estimation of the temperature in each of these layers, for example in the gold and in the platinum layers. So here we can use a first order approximation, because of both gold and platinum are metals and work well with this kind of formula. So we have calibrated our system, and we can find how much is the resistance and how is the linear constant for platinum and also for gold. And with this, we can estimate the temperatures in our system, and also calculate how much is the thermal gradient through the silicon oxide insulating layer. This is very interesting, and if we also are able to estimate the thermal conductivity of GFO by using the 3 omega method, this has been done in SICUS in Santiago de Compostela. With all this, we are able to estimate all the details, all the properties of the system in a more controlled way that is normally done in literature, with bulk samples instead of devices. So now we can benchmark our GFO comparing it to jig. So we can observe here that we have a system with a comparable voltage, thermospin voltage, when we compare with jig. But you can also observe here that there is a small shift in the hysteresis loop as a function of the heater applied here, and we can argue that this might be induced by pyroelectricity, but this is still an ongoing work, so we are not completely sure about this. And I hope I convince you that GFO is a very interesting material for spintronic applications. To sum up, we have studied the spin magnetoresistive effects in GFO. We have achieved the growth of this multifunctional material with high crystalline quality. We have observed that the spin Hall magnetoresistance is dominant at all the temperatures and comparable to the jig platinum heterostructures, and we have also shown that GFO can be used as this multifunctional material in different applications. And in terms of the thermospin transport, we have fabricated these thermoelectric devices with a high local thermal gradient, and we have been able to quantify the heat flux and all the relevant parameters in the system to be able to really quantify and compare between different systems. And we have observed that the spin-Seebeck effect in GFO platinum is comparable to the one that people typically observe in jig platinum heterostructures. And with this, I want to thank to all my collaborators.